Okay.
My references.
Okay, thank you very much. So it's an honor to start this series of postdoc. Of course, it's just because my name starts with a B and with an O. But anyway, it's nice. So I'm going to talk about stability and instability of near-integrable Hamiltonian system. So here's the plan of my talk. First, I will recall the definition, or I will state the definition. Then I will just state three fundamental results. I call them K, A, N. It's because they are due to Kolmogorov, Arnold, and Nekoroshev. It's not going to be in this talk, sorry. And finally, I will mention three questions I'm currently interested in. Okay. So let me start. So I will explain what is an integrable Hamiltonian system. I mean, just for me or for the purpose of this talk. So I'm going to consider dynamical systems. So the phase space is going to be the cotangent bundle of the torus. Okay, it's just Tn times Rn. This is going to be my phase space. And I consider a function defined on Tn times Rn. We're going to Hamiltonian function. And to this function, I will study these systems of differential equation. Okay, these are Hamiltonian differential equations, so these are the usual forms. And this is going to be my my object of study today. Okay. So I will give name to these coordinates. I will call them angle actions. Okay, because I'm going to use it after. So theta are going to be angle. They are on the n-dimensional torus, and I will be called action. It will be they will evolve in Rn. Okay, so in this simplified setting, so what is an integrable system here? So integrable system is going to be a Hamiltonian function which depends only on half of the coordinates. Okay, that depends only on the action coordinates. And so if you take this Hamiltonian and you plug into this differential equation, you can see you can easily solve this differential equation. And the solution, so I will denote it by theta t I t. So you can solve them explicitly. And what do you obtain? So the first thing is that the action variables it are integrals of motion, okay? Which means that they stay fixed for all time. It doesn't evolve. So that's the first thing. That comes from the second equation. It's because I dot equals 0 in this case. Okay? The second thing is the tori Tn times I naught are invariant. That's exactly the same thing as the first one. Okay, it comes from the second equation. But you have also the dynamic on each torus. So the dynamic is quasi-periodic. It means that the evolution of the angles are just linear. Okay, you have a linear flow on each of these torus. Okay, so that will be the integral system I'm going to consider. Okay, I have a collection of invariant tori, and the dynamic on each tori is a flow of translation. Okay, so this is very easy. Okay, I have nothing else to. There's nothing else to say about this this case, this integral case. So now in practice, what is more interesting is that is near-integrable system, which means perturbation of an integrable system. And how I perturb an integrable system? So here's the integrable part, and I just add a small perturbation. Okay, so to be more precise, I will have to speak about topology of function space and so on, but I'm going to be very sketchy, so I just put epsilon in front and I add a general function. Okay? And now the general problems of the dynamics according to Poincaré is the following: is to compare the solution of this Hamiltonian system associated such functions to the one of the integrable systems. Okay? And in this talk, I'm going to be more interested in this question here. So in particular, for solution theta t it of star, this time now I'm considering only this type of systems. So there's two types of questions you can ask. Simple question. Does it stay close to its initial condition I0? Okay. I recall that they are constant for the integral part. So if you perturb, you want to know if they are almost constant. In this case, we'll speak about stability. Second thing is, does it move far away from its initial condition? Okay? And in this case, this will be more or less instability. Of course, this is not very precise for the moment, but I'm going to be more precise later on. So that's basically what is stability and instability in the title of my talk. So why do people study this type of problem? Let me give just a motivation or historical motivation, sorry. It is related somehow to the stability and stability of the solar system, okay? So how? So first, I recall what is the n-body problem. You take n particles that interact with each other with the gravitation law. It means that the attraction between two particles is proportional to the inverse of the square of the mutual distance and to the product of their masses. Okay? So this is Newton's law. And so for n equals 2, this can be solved explicitly somehow. Trajectories are ellipses, okay, with negative energy if you want. But for n equals 3, not much is known, in fact, about this solution. Very few is known. Well, what is known is even for n equals 3. N equals 4, 5, it grows and grows. And it's very difficult. So there's a particular type of n-body problem we can consider is the planetary system or the solar system. In this case, it's a 1 plus n-body problem. So why do I make a distinction? It's because I have the sun and the planets. Okay? And the sun is much more bigger than the planets. Okay? So in this case, the attraction of the sun, recall that this is proportional to the force of interaction. So the attraction of the sun is much more important than the interaction between the planets. Okay? So what I can do in this situation, I can first neglect the interaction between planets. Okay? This is an approximation. I make an approximation of the system. I neglect the interaction between planets. Then in this case, I have an integrable system. Okay? I forget to say that for n equals 2, the system is integrable here. Okay? So now here, what do I have? I have n uncoupled two-body problem. Okay? I have just the sun with each planet. The planet doesn't see each other, if you want. And in this case, I'm back to the two-body problem. If you want. Trajectory are ellipses. I can write my system in angle action coordinates, as I explained in the beginning, as I said. And in this case, the action variables, so they stay constant, and they depend only on the semi-major axis of the ellipse. Okay? And since in this approximation, this is the Kepler approximation, trajectory are ellipse, of course this stays constant. Okay? So that's a meaning of what is the action variables in this case. Now, if I consider the interaction between planets, because it is small but it exists, okay? Now the system is near-integrable. It's a perturbation of an integral system. Epsilon is stay minus 3. Okay? So that's the size essentially. And studying the evolution of the action variables that were constant here is a way of studying the deformation of the ellipse. Okay? So it's a way of knowing if the trajectory is stable or unstable. Okay? So that's the motivation. So now let me go to the three fundamental results I was explaining, K, A, N. So the first one is K for Kolmogorov. Is the following. So you take H as in star, so this is near-integrable system. You prescribe an open ball in the action variables because I'll need to have a bounded part of the phase space. And you assume some condition, so H non-degenerate. So I put, there's going to be a lot of quotation mark. I'm not going to explain in details what it means. You assume some regularity on the system. You assume here in this case, let's say it's analytic. Then the outcome is, if epsilon is small enough, epsilon is the size of the perturbation. Then most solutions in this ball, with initial action in this ball, are quasi-periodic, like in the integrable system. Okay? So I have to say what is most. So most basically is this. Okay? It's something which is large in the sense of measure, but small in the sense of topology. Okay? So positive Lebesgue measure, but meager in the sense of Baer. So what is the consequence of the theorem is that most is the same most as this one. Solutions are stable. That is that the action variable, so I'm interested in the evolution of this action. They stay almost constant, a quantity that depends on epsilon, for all time. Okay? This comes from this theorem, from a quantitative version of this theorem. Now, in fact, this is true for all solutions for n equals 2 under different non-degeneracy assumption, essentially. This is due to Arnold. So for n equals 2, this is every solution is stable, essentially. So what happens for n equals 3? So that was the question. For n equals 3, this does not hold. Okay? So this is due to Arnold, which was a student of Kolmogorov. And the result is the following. So for n equals 3, there exists an analytic system with H non-degenerate, such that for all epsilon strictly positive small enough, you have one solution and the time tau, which depend on epsilon. Of course, everything depends on epsilon, for which the variation of the action is not a quantity that depends on epsilon. It's big, bigger than 1. It can go to infinity, of course. So this is what is called Arnold diffusion sometimes, or Arnold instability. So Arnold example, so this theorem, this is a weak instability, I put quotation mark, because it says basically that you can go along one direction. You can expect much more, and much more is expected, but we don't know yet for the moment. For a specific perturbation, here there is one, okay, one perturbation. Now along Arnold example, there's Arnold's conjecture, which said that you have general instability. I'm not going to explain why, maybe later, I'll give an example of what would be general instability for a typical perturbation. But this is a very difficult question. A more tractable question is that, and it's a reason why it's difficult to show this type of phenomenon, is how large is the time of instability, this time tau, okay? The time you have to wait until you can see this phenomenon appears. Of course, it goes to infinity when epsilon goes to 0, but how fast? Okay? So that was a question of Arnold, basically. And this was, first answer came from Nekoroshev, which was a student of Arnold, so that's why I put KAN in this order. And the setting of the theorem is essentially the same as the one of the theorem of Kolmogorov. So you take H, you fix an open ball in the action. You assume there's a different non-degeneracy condition, but I'm not going to explain that. So non-degeneracy on H, regularity on the total system. That are the common assumptions, okay? And in this case, the outcome is that if epsilon is small enough for all solutions, you have stability somehow. So just now with epsilon to some power b. B is strictly smaller than 1/2, in fact. So this is true for all solutions. But of course, now you cannot have this for all time because of the example of Arnold. But you have this for a very long interval of time, okay? For an interval of time which is exponentially large with respect to the inverse of epsilon, okay? With some exponent a. So now let me compare briefly this theorem with the one of Kolmogorov. Kolmogorov's result is probabilistic stability, okay? If you pick an initial condition at random with respect to the Lebesgue measure on the ball you prescribe, then with large probability it is quasi-periodic, okay? For the others you don't know. Now Nekoroshev result is effective stability because it applies to all solutions. Of course it gives a much weaker statement. But from a physical point of view, this is, I mean, this depends on the point of view, but it looks more physical, maybe, this one. Okay? So now consequence on instability is that the time of instability tau epsilon is extremely large. Okay? It is bigger than this quantity. Okay? So now let me finish by 3 brief questions in order of difficulty somehow, maybe. The first one is transition between stability and instability. Okay, let me explain what I want. Is what are the best time of stability, capital T of epsilon, and time of instability, tau of epsilon. So here's a picture to understand. So you have a result that say that during some interval of time, this is time scale if you want. You have blue means stability. It means that the solution does not move a lot. And after some time, it is possible to have instability. This is in red. So the question is, where is exactly the transition? Okay, time like this. Where exactly this this mark here? Okay. So let me say this is known when H is linear. Okay, you know exactly where it is. This is almost known when H is convex. There is a small gap somewhere here. But not much is known for the other case. For the other case, you have some results here, but they are not the best, I think. And it's complicated to construct example of Arnold diffusion to test that. Also, one can ask the same question for a generic perturbation. Because example here usually are very, very, very specific. And maybe for a generic perturbation, this goes, stability should be longer. And okay, I'm not going to explain more of that. This question. So now a second question, it's about realistic stability estimates. So in fact, the result of effective stability, type Nekoroshev theorem, do not apply to concrete systems, like three-body problem, for instance. It does not apply. There's many reasons why. I'm going to explain briefly. So here the question is just try to apply a result, because it's a pity that you can prove theoretical result, but you cannot come back to what is the motivation of the problem. So there's many problems, but one of them is the following, is that theoretical results are valid for epsilon small enough, okay? That is for epsilon smaller than some quantity which depends only on the system. But in practice, in the problem, this is not satisfied. Okay, this is not satisfied. If you want, in the theoretical results, the philosophy is that epsilon is a free parameter that you have the right to take as small as you wish so that your theorem applies. In practice, this is not the case. Okay? So one possible strategy is to try to weaken the stability result I explained as much as possible as to make it applicable. Okay? Another strategy would be to consider explicitly the system, the concrete system, and to try to prove the theorem in this case. In celestial mechanics, there's too much computation and it doesn't work most of the time. It's very difficult. So one possible statement one can prove is the following, is that for H convex, we can take three parameters, rho and k, and in this case, there is a threshold epsilon 0 which depends on rho and k, such that for epsilon smaller than this threshold, we have this weak stability result. Okay? So why does it have some interest? Maybe it's because now we have some more freedom in this result. The hope is the following, is that we can take rho very big and k very small. Of course, taking this is much, this becomes more and more weaker. But the threshold grows, okay? And so maybe we can hope to achieve such a relation, okay? So to conclude, let me mention, so the last question will be about new mechanism of instability. So this is a fact too, if you want. All mechanisms of instability are essentially the same, following Arnold or matter, if you want. So you have two pieces. So you have the skeleton. First, construct existence of invariant sets with good properties. It can be hyperbolic or minimizing, depending on the method you use. And then you give flesh to the skeleton. So this terminology is due to Rorschach. Okay? It's the existence of an orbit that follows this path of invariant sets. Okay? Almost all of them, with very slight difference, it goes this way. So this is very nice. Along this way, what can do? We can construct example like Arnold, weakened stability for a specific perturbation. We can do better than Arnold example. Of course, it's 50 years after. So, and what we can do also, I mean, this is just announced results, is that you can have weakened stability for a typical perturbation. But this is much more. But what I term general instability, this does not work. I mean, it has been tried, and it seems that new mechanisms are required for these questions. So as an example of what I mean by general instability, is that the following question of Hermann is still unsolved. Is that construct a smooth Hamiltonian H, Ck close to the most simple integrable Hamiltonian system with 3 degrees of freedom, this one, which has a dense orbit on an energy level. It's much more stronger than this weak instability. And it's no one knows. It requires certainly new ideas, maybe coming from symplectic geometry. That's the topic of this year. So I'll finish now. Thank you.